we can rewrite as e to the 3t times, iu2 plus t times a minus 3i u2 plus dot, 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 right? And that works out to what? E to the 3t times u2 plus tu1. Which explicitly is what? It is, let's see here, t e to the 3t for my top component, and then e to the 3t for the middle one here, and 0 down there, right? That is a solution that we could not have found before today, unless we took an ad hoc, like solve and substitute kind of method kind of thing, right? Are we done? Well, no. We're trying to find the general solution as usual, right? We're not there yet because we only have 2 linearly independent solutions. I still need a third. So what should we do? We want what? We want u3 not equal to 0 such that what? Such that a minus 3i times u3 equals to what? Not u1 this time, but u2. This is the chain condition. So we want to solve that equals to u2. And so that becomes 0, 1, 0, 0, 0, 1, 0, 0, 0 times uvw equals to a 0, 1, 0. All right. That gives me what? What equations am I up against here now? Top equation there is v equals to 0. Well, v's back to 0 again. That's good. Next equation, w. Looks like w's got to be 1. And u, again, as usual, free. I suggest, again, we make u equal to 0 because we can. And if we do that, this tells us that what? I should make u3 equal to 0, 0, 1. And in this case, if I do e to the ta times my u3 and I work it out, I get e to the 3t times what? Times u3 plus t times u2 plus 1/2 t squared times u1 from the magic formula. That follows from the algebra I did over here, right? Like for the u3, when we hit u3 with just one copy of a minus lambda I, we get the u2. When we do 2 copies, we get the u1. And so like the 1 copy of a minus lambda I has the t in the formula. 2 copies has the t squared. And that's like, sorry, I run out of space to put the details here. Are you guys, want me to write them out, the details, or do we understand what I did here? It's your class. I can write them out if you want to. Okay. So, in short, then, my general solution has the following form. R of t is c1 e to the 3t. And I'll factor out the e to the 3t so I don't write them so many times, guys, if you don't mind. And then plus c2 e to the 3t. And that one's got a t, a 1, a 0. And then plus c3 e to the 3t. And that one's given me a 1/2 t squared up here, a t there, and a 1 down here, like so. And there you go. That's the general solution to this problem. Any questions? Excuse me. So because the linear algebra here gets really a little bit tedious for like in-class test, I like to ask questions on this material which are more symbolic in nature. So I'm really just testing on your ability to understand the magic formula and to assemble the solutions using the chain condition. So let me look at an example like that where the matrix is not actually given, but we have like symbolic information about it, all right? And I'll throw in a complex eigenvector to boot. All right, so here we go. Example 4. Suppose we have a minus 3i times u1 equals to 0. We also have that a minus 3i times u2 is equal to u1. In addition, we have a minus, say, 2 plus 7i times I acting on, let us say, u3 is equal to 0, and a minus 2 plus 7i acting on u4 is equal to u3, where u3 is a3 plus ib3, and u4 is a4 plus ib4. All right, I think this is sufficiently horrible. Let's find the solution. How big is my matrix? To make this meaningful. I heard a 4 by 4, but be careful. If this is a real matrix, I should tell you A is a 1, 2, 4, 6, 6 by 6. So like, I can look at this information and I can tell you that these two tell me that actually my characteristic polynomial it would be equal to like lambda minus 3 squared, and then this is going to give me a yowzers, lambda minus 2 quantity squared plus 49 squared. Like that's where this problem would come from if you had a characteristic equation which was 6th order like this, with a repeated complex value. All right, so we're looking for 6 linearly independent solutions. 2 of these I've kind of already talked about already. So like we could do e to the ta times u1. What's that give me? u1 is an eigenvector, right? So that's an eigensolution. I know that this is going to give me, e to the 3t u1. So that's one solution down. Great. Of course, you don't have to write this down, right? Logically speaking, you could just write down e to the 3t times u1 is a solution. We know that. It's an eigensolution. We already have that. Great. And, of course, e to the ta times u2 is e to the 3t times u2 plus t times a minus 3i u2, right? Which is what? So let me start numbering these as we find them. Solution number 1, solution number 2. We got to find 6 of these, right? So then what? Well, from this, we have a complex solution. I'll get straight to the point here. E to the 2 plus 7i times t, right? Times u3. Which, remember, this is e to the 2t. You got your cosine 7t plus I sine 7t times A3 plus IB3. This gives us the kind of solution we talked about last class, right? It's got this a and b terms. It's got a minus because of the I squared. You factor the I out on the other term, all right? And gleefully, we can't put numbers in because we don't have them, you know? So all we can do is write this symbolically, which is, I think, plenty. So there's solution right here, number 3. And over here, not including the I, without the I, okay? Here's 4. I've got 4 linearly independent solutions now. So what's up next is the complex eigensolution. So I also can write, we call this Z1. Z2, we can do e to the TA times my U4. All right, but that's equal to e to the 2 plus 7i t times U4 plus, you know, t times U3. The same, I'm running out of time here to write everything out, but it's the same magic formula with a complex lambda rather than a real lambda, and everything still truncates past that because U4 is a complex generalized complex eigenvector with eigenvalue with order 2. So like the squared terms, the cubed terms, those all vanish. We're just left with that, which then gives me e to the 2t, you got your cosine 7t, plus I times the sine of 7t, times a4 plus t a3 plus I times b4 plus t tb3. All right? So here's the answer. R of t is C1 e to the 3t U1 plus C2 e to the 3t times U2 plus TU1 plus C3 e to the 2t cosine 7t A3 vector minus sine 7t B3 vector plus C4 e to the 2t sine 7t A3 vector plus cosine 7t B3 vector plus C5 e to the 2t cosine 7t A4 plus TA3 minus sine 7t B4 plus TB3 plus C6 e to the 2t sine 7t A4 plus TA3 plus cosine 7t. Oh, why did I do this? B4, I mean, I guess I asked you something like this in the homework, so just be nice. TB3. And there you go. That's the solution. Yeah. Yes, it would be on the test. There we go. I know where you're going. Well, I mean, do I want to grade this? Not really, right? But do I test these concepts on the test? Yeah. So, I mean, I can, like, to make this problem less annoying to grade, I just make it about just this or something as opposed to like all of this, or, you know. But there is a problem like this in your homework at least. Yeah. Uh-huh.
For the problem in the homework like this, I assigned like the different, I think I assigned up to like, I just used like a different variable for like all of them, but I like set up equals to
Hmm.
So like instead of writing it all out, I just had like R of t equals c1 x sub r like 1
Yeah.
plus
I
x sub r2.
I don't know. I'd have to look at it, but I mean, this is the only way I can write this solution out because I don't have numbers or anything, right? I just have these letters to work with, so symbolically is like all I can do. Anyway, so next time, guys, we'll finally talk about the non-homogeneous problem, and we'll see that variation parameters lives again. Woohoo!